Hello class, so this is CSE 5250, Section 2, Week 2, Spring 2023. Per the announcement that I made in class and on Canvas, I want to have the class be a hybrid class, so instead of having us meet twice a week, we instead meet once a week and have an asynchronous video lecture that you can watch in your own time. And the following class meeting will be an opportunity to ask questions about anything that we might have. So this will be the first of, well, many video lectures. And the first thing I want to talk about is the pseudocode for the sieve of Eratosthenes. This was something that was requested, so let's walk through this code together. So this is an algorithm that was described in ancient times by, well, a Greek mathematician by the name of Eratosthenes. And this is an algorithm that looks for prime numbers from 1 to a specified maximum number. For our purposes, let's say it's 10,000. So how does this work? Well, we can make an array of integers from 1 inclusive to the max number inclusive. So 1 to 10,000 and all the numbers in between. We have a for loop that iterates through the array, looking for numbers that are not marked as non-prime. So by that, I mean any number that we haven't eliminated as non-prime. Since this is an array from 1 to 10,000, we don't have the number 0 popping up anywhere. So for our purposes, we can use that number to signify a number that was crossed out because it was non-prime. I previously taught this using a two-vector approach. So one vector would have all the numbers, another vector would have an array. Yeah, another vector would be, it's basically an array of Boolean values. So I would just set those values from true to false to signify, hey, this is not a prime number. By using a singular array, it makes the code a lot simpler, I guess you could say. So we enter the outermost for loop, and we have this here. We're going to have an index. We're going to have an index that's going to go from 0 to the square root of the maximum number. Here I chose the number 10,000 because it's easy to find the square root of that. It's 100. There is a mathematical reason why as to why we don't have to go from 0 to the max number itself. I'm going to leave that as an exercise for you. But it has to do with the fact that it has to do with how the factors of it's something to do with the factors of numbers. But anyway, we don't have to go through the entire array for the outermost for loop. We only have to do that for the innermost for loop. Okay, so one other step we have to do before we enter this for loop is to set the first element in the array, which is 1, to 0, because 1 is, well, not considered to be prime. So when this outer for loop starts, it's going to take the current prime, which is going to be, it was supposed to be 1, but it's 0. It means this condition is going to fail if current prime is not 0, but is 0. So this condition is going to fail, so we don't have to enter the inner for loop. So we iterate to the next number, which is going to be 2. That is non-zero, so we get to enter the inner for, we get to execute the inner for loop. For index 2 in the range index to the max number, the current number is going to be the element at index 2 in the array numbers. this for loop is actually going to start at the same position as the inner for loop starts at the same position as that the outer for loop is currently at, is what I'm trying to say. So if we're at the number 2, the inner for loop is going to start at the number 2. Or rather, it's going to start at the index that corresponds to the number 2. So the current number is 2. The current number, if the current number does not equal the current prime, because we don't want to cross out the prime numbers themselves, we only want to cross out multiples of the prime number. And we don't want to cross out multiples. We don't want to cross out the prime number itself. 2 is a multiple of 2, but it's like a trivial multiple. So we want multiples of 2 that are greater than the number 2 itself. So this condition has to pass. So we don't want to cross out 2 itself. This second condition says if we divide the current number by the current prime and we get a remainder of 0, that means the number is divisible by 2, so replace that number with 0. So we try this with the current number being 2. It's going to fail this condition here, so we go to the next number, which is 3. It passes this condition, but it actually fails this condition because 3 divided by 2 leaves a remainder of 1. So I have to go to the next number, which is 4. It passes the first condition, and it passes the second condition. If we divide 4 by 2, we get a remainder 0, so we get to replace the number 4 in the array with a 0. And we repeat that process for all the other numbers from 4, 5, 6, all the way to 10,000. At that point, the inner for loop completes. And then we get to proceed with the next iteration of the outer for loop. So if you can imagine, we have the number 2. Its multiples have been crossed out already. 1 was already crossed out because we had to say that it is 2. The next number after that is 3. And that has not been crossed out because we crossed out 4 and 6 and 8, but not all the numbers but not any of the other numbers. So the current prime is going to be 3. And then we can enter the inner for loop again. The current number is going to be 3, so it fails this condition here. So I have to go to the next number, which is, it's supposed to be 4, but we crossed that out. Is that going to be a problem in here? Well, let's see. 0. The current number is actually going to be 0 when it's supposed to be 4. So 0 does not equal 3, so it passes this condition. And 0 divided by 3 is going to be 0. So it's going to redundantly replace 0 with 0. But that's okay because it's going to replace the number with the same number as before. The for loop might do a little bit more work than we wanted to, but I'll talk a little bit more about that later on. The next number is 5, so it passes the first condition, and it's actually going to fail the second condition because 5 mod 3 has a non-zero remainder, so I have to go to the next number, which is 6, but that was also 0. So the next number is 7, and that fails the condition. Next number is 8, which is already crossed out. So, which technically passes both conditions. So let's skip that and go to the number 9. it passes the first condition, and 9 divided by 3 leaves a non-zero remainder. So this is the first number that we found that's going to be replaced with a 0. By that I mean, there were a few multiples of 3 that were also multiples of 2. Those were already crossed out, so we're going to cross out multiples of 3 that we haven't encountered yet. This should make sense, because if you think about it, the multiples of 3 have some of the multiples of 3 are also multiples of 2. So some of the multiples of 3 have already been crossed out because they were multiples of 2. Okay, so we cross out the number 9 because that was divisible by 3. So 10, 11, 12, 13, 14, 15 gets crossed out. 16, 17, 18, 19, 20, 21. There are some numbers that don't get crossed out though. So this process continues until we've basically processed the entire list of numbers. So at the end we should have all the prime numbers between 1 and 10,000. Now there is a faster way of doing this inner for loop. And here's how. Instead of iterating through the array one element at a time, we increment by the current prime itself. So by doing this, we eliminate this condition that we have to check for. Does the current number divided by the current prime have a remainder of 0? Because if we start at 2 and we go up by 2, if we start at 2 and we increment the iterator by 2 each time, every number that we encounter is going to be a multiple of 2. So we don't even need this condition at all. So we only have to check for one condition, and it's this. We only have to check for this, if the current number does not equal the current prime. So this is the modified inner for loop. We need to write it a little bit differently, but if you're to write this in C++, you'll realize that you just need to change the increment portion, the update portion of the for loop statement. That's going to be I++ or J++. You have to instead have something like J plus equals current prime. So that's the pseudocode for the sieve of Eratosthenes. The next thing I'm going to show is what that would look like in code. So I'm going to open up Visual Studio and write a bit of code. I'll pause the recording, and just like that, I have the code for the sieve of Eratosthenes realized as C++ code. So here's the outer for loop that iterates from 0 to the square root of the search max. That's the outer for loop. Here's the inner for loop. Here it is. We start with J set to I, and we iterate through the whole array, so it goes to search max. But we iterate for the update step here, instead of having something like J++, we have J plus equals current prime. So just like that, we did a few optimizations for the sieve of Eratosthenes. How are we sure that this thing runs? How are we so sure that this algorithm runs faster than if we had it differently, such as like this? Here, the inner for loop iterates by 1 each time, and we have to do that check where we have to make sure that the number we're looking at is divisible by the current prime. Well, how do we know if it's faster? We do like a stopwatch reading. So there is a way of using something called chrono to let us get the execution time of the entire program. So let me quickly implement this. You get to watch me do this live, you get to watch me do this live again. So let me just read this off. Okay, for our purposes, I'm just gonna define execution as the start right before we execute this very line of code, and for our purposes, I'm going to define the start of execution as right before this line of code and right after we've exited the for loop. I'm not going to count printing as part of the execution time, though. So let me just write this code. So auto start equals standard chrono high resolution clock now. And then I copy this, paste it here, call this stop, and then I get to calculate the difference between the two. So auto exec time equals standard chrono duration cast, and then in the angle brackets standard chrono microseconds, and then in parentheses stop minus start, and that'll give us the execution time. So let's print it out. So you can write something such as this. You have to write down exact time dot count, not exact time by itself. And then yeah, I'll go a little more in. We don't have to time our execution time. We don't have to time the execution times right now. We will get into that when we start benchmarking this algorithm. For now, it's good to know what it looks like, because then we can see execution times. So it took 16,000 microseconds to compute, so what is that, 17 milliseconds? If I change the code back to this configuration, so and then I don't need this condition anymore, so I can just remove that. Just like that. That one small change reduced the execution time from 17 milliseconds down to 5 milliseconds. So that kind of change adds up when we're looking at larger and larger search maximum values. So if I made a really large number and tried it, then you can see how slow this program becomes. That took what, 5 seconds? So the question we'll be asking ourselves later on is, can we make this parallel? How can we make it parallel? And how much of a speed boost do we get out of it? Can we measure the speed boost? How much of a speed boost can we theoretically expect? So those are a few things we'll be asking ourselves later on when we start, well, benchmarking this thing. But for now, I want to start talking about OpenMP. So for that, I'm going to need a new project. So the reason I need a new project is because if you're going to be using Visual Studio, you actually have to go into the settings and specify that you want OpenMP support. So let's see what that looks like. Alright, so I have a new project. I'm going to add a new item that's going to be my main.cpp. Okay, now let's do one change in the settings. So I have to move my webcam for this. So here we are. We have to right click here and then click on properties. Hold on, it's not showing up yet. Give me a bit. Okay, now I find it. We actually want to click here. Here, if you can see it now. We click here, properties, C/C++ under configuration properties. And under language, there is a setting called OpenMP support. Set that to yes. Apply. Okay. And now we can start playing with OpenMP. So let's write a hello world program as we normally would. So okay, write a hello world program and it just says hello world. But now I get to do this. I include this omp.h. So that's going to include all the multi-threading stuff that we get to use with OpenMP. So if we just run it again, nothing new happens. That's because I need to define a region of code that's going to be parallel. So I do that by doing this. I define a region of parallel code by using this thing here, pragma omp parallel, and then I need to put in some curly brackets to enclose the code that I want to run on multiple threads. So if I run this now, what happens? It says hello world 16 times. Why does it run hello world 16? Why does it say hello world 16 times? Why? Because, well, for my main computer has an 8-core 16-thread CPU, so it's going to run one thread for every CPU. It's gonna run one thread for every logical processor that I have. So that's how I got 16 hello worlds. Let's experiment a little bit now. I'm going to add in two more functions to this, and that's going to be OMP get thread num. That's going to call a function from here that's going to get the current thread number, but I have to store that in a variable, so int. So I have to store it like that. I'm going to add in another function called this. This second function is going to get the maximum number of threads that's available. This is going to get me the number of threads that the program is using. So it looks like this. And I'm gonna have to store that in a variable, so int. We have thread number and max threads. So with this information, let's modify this hello world program so that it says something like hello world from thread such and such out of some other number of threads. So let's write that. Let's try this out. So what I expect to see is hello world from thread number of max threads. As you can see, it's all scrambled. So hello world from hello world from thread hello world from thread 3 of 16. So the problem is all 16 threads are trying to print stuff to the screen all at once. How this works is these pieces here. The best way I can explain it is we have these pieces being printed to the console one piece at a time, and all 16 threads are trying to do that all at once. So later on we'll look at ways of synchronizing threads so we don't have. That way we can enforce some order in which threads. Yeah, that way we can enforce some order in the order in which threads execute. For now, what happened here is what is an example of a race condition. So there's an order in which these threads, as I said, print this entire statement here. But because every thread is trying to print all at once, they're gonna run over each other, so to say, and we get stuff like this. But it's also a mess because I didn't add a end line at the end. So actually I'm gonna make it worse by doing this. And it almost works. But if I run it again, the order is a little different from before. Yeah, this is one thing about multi-threaded This is one thing to keep in mind. There's no order in which these threads execute. So if we want to do things in order, we have to find a way to enforce that order. We need synchronization. But for now, we're going to look into that a little bit later. But for now, I'm going to keep these threads from overlapping with what they're saying. Hello world from thread, hello world from thread 10 of 16. I'm not going to use cout, and I'm going to instead write it like this. And /n. Okay, we're getting there, but I forgot to comment this out. Okay, there we go. So at least now every thread is printing its own line. The best way I can explain it is this is printing everything all at once, whereas if I had it C out, it's going to print it all as, it's going to print it part by part, at least the way I have it written here. So perhaps another way is to just assemble an output string like this. I can then copy that. Concatenate these parts together. And then I can't have this, so I have to write like this. Does this make sense? The compiler says, it says no, this does not make sense. So, let me try to fix this. Well, I can tell you right now that doing it like this doesn't work. So, if we want this print out messages, we're gonna want printf instead. Okay, so I also have one more thing I want to show, and it's going to be this quick start guide that I'm going to have available on Canvas later on. So this contains a few example programs that we can try out for ourselves. So the first one, I'm just going to copy all the code, and paste it. What does this do? Well, it's going to add these two vectors and store the result in a third vector. So we have vector A and vector B. We add 1 plus 10 and store that result as 11. We have 2 plus 9, and that's also 11, and we store it here. And we repeat that process for all the other pairs of numbers from A and B. So we can realize that in code with this simple for loop here. Add vectors A and B and store the result in C. If I run this right now, this last for loop will print out the result, and we get an entire vector full of 11s. So, one thing we can do to make it parallel is using a parallel for loop. So, we can make this parallel really easily. Watch this. And boom, just like that, it runs the same as before, but just take my word for it, this thing really is, actually, no, I actually forgot one thing. It's this. How do we know for sure that this thing really is running on multiple threads? I could do this. And then I can just write in this. the reason I'm writing this in is because I want to know for sure that this section of code really is parallel. Oh, whoops. If it is really running parallel, then I should see something like thread 3 calculated something plus something. And I should see that for different, I should see that for various threads as well. So if I run this again, yeah, it is running parallel. So because we only have 10 sums to compute, and I have a maximum of 16 threads available to me, I only needed to use 10 threads. So those are thread IDs 0 to 9. They're each concurrently calculating something plus something, and they're each gonna store that in some element of vector C. Alright, so as I said, this is just a really basic example of vector addition using OpenMP. This is only 10 addition operations, so it doesn't look like we're doing all that much of a difference. But imagine if we had larger vectors like that. So instead of like 2 vectors of like 10 elements, we had like 2 vectors of 10 elements each. We had like 2 vectors of like 1,000 elements each. But one step up from vector addition is a dot product. So I'm going to copy another sample program from here, and let's walk through it together. So if I copy that, paste that all in here. First, let's take out that directive and try to run this as we normally would. So what's a dot product? So we have these 2 vectors again, and instead of adding these 2, we multiply them and store that sum in some value. We multiply these 2 and take that sum and add it to that previous value. Multiply these 2 and add that to... So the dot product is going to be this value here. We start at 0, multiply these 2 together and increment and add that value to here. Multiply these 2, add to here, multiply these 2, add to here, and so on. And that's what this for loop is for. And then we're going to print the dot product. So we get a dot product of 220. So what happens if we make it parallel? Well, we're going to introduce a problem. Well, as you can see, that actually executed normally, but if we run it again, you see the problem now? It didn't get 220, it added to it got it to 154 instead. But depending on when I run it, I'll get 220, or I might get something that isn't 220. And here's the problem. All 10 threads are trying to add something to this dot product value. But they're all trying to do it all at once. If you recall from operating systems, you may have heard about this problem. We want to maintain what's called mutual exclusion. That is to say, one thread has to increment dot product at a time. So all 10 threads could calculate the dot product. No, all 10 threads can do this multiplication operation on their own, but when it comes time to add that result to the dot product, that has to be done one at a time. So we say that this is a critical section, and we can define it by adding this compiler directive called critical. This will define this single line of code as a critical section, or if we had multiple lines of code that was part of a critical section, we could have something like this. Enclose the code in curly brackets. So if you run it now, we should get 220. And if I run it again, I should always get 220 every single time. So yeah, that is how to get started with OpenMP. I'll have this quick guide available on Canvas, but one other thing. What if you were to compile this using a Unix terminal? Well, let's enter that right now. So first, let's add this include omp.h. Then let's try to compile it using a Linux compiler. So let me just close these first. To that, I'm going to simulate that process by opening up Windows PowerShell. I'm going to change directories. So so that's not going to work. Hold on. Instead, actually what I want to do is, if I want to open PowerShell, if I want to open PowerShell inside a specific Windows folder, I just type in PowerShell into the address bar up here. So what compiler command do I need to type in if I want to compile a this is the code that has all the OpenMP stuff that I want to compile. So what do I type in? The answer is this. Hold on. It's G++ dash O. I'm gonna call it main dash F open MP and then main.cpp. Does that work? Yes, it does. Dot slash main, and there we go. It ran the program that I compiled, and it gave me an answer of 220. A few more other things, by the way. If I go back to the Hello World program that I had previously, which is this, you'll notice that I have 16 threads running because, well, that's the number of threads that my computer can support at a maximum. Thing is, we can actually specify the number of threads that we want to use. So that would look like this. So we add in this function here. Set num threads. Let's type in say 4. Then if I run, I should only get 4 threads, and therefore 4 hello worlds. But can I go over 16? I used to think that you couldn't, but apparently you can. So let's try 32. And it does work. We can have as many threads as we want. It's not limited, as I initially thought, to however many logical processors that we have. So we can have as many threads as we want. So that would be interesting to have a lot of, it would be interesting to have a lot of threads like this, but at that point could be actually run all 32 threads at once. That's another open question for you. So what I'm going to do is I'm going to upload the pseudocode here. I'm also going to upload this quick guide here. I'm going to add the Hello World program to this. I'm also going to add instructions on how to compile an OpenMP program on a Unix terminal to here. I encourage you to try this out for yourselves. We'll meet back on Monday in person to discuss any questions that we may have, and this is basically the part where I have you try to experiment with these programs for yourselves, because one of our first assignments is going to be to try to write an OpenMP program that does something. One thing I'd like us to do is try to write a matrix multiplication program using OpenMP. So try this out and see how far you can get, and then we'll meet back on Monday to answer any questions. Alright, see you next week.